Welcome to Spaceverse, your portal to cosmic adventures. There are many who believe that the Andromeda galaxy is speeding towards Earth with the purpose of merging with the Milky Way in a few billion years that will result in the formation of a single massive galaxy. This cosmic collision has actually begun, which may seem like an unbelievable thing to believe. Not only have scientists observed the halo of the Andromeda galaxy pressing up against the halo of the Milky Way galaxy, but they have also provided the first proof that these enormous galaxies are trading stars. Both Andromeda and the Milky Way are the two galaxies that are considered to be the most massive among the approximately 80 galaxies that comprise the local group. With the Milky Way and its satellites forming one lobe of the local group, and the Andromeda galaxy and its satellites forming the other, the local group can be thought of as a dumbbell-shaped structure. There are around 3 million light-years between the two clusters, and they are moving toward one another at a speed of 123 kilometers per hour, which is equivalent to approximately 76 miles per hour. At this very moment, we are witnessing the beginning of what is going to be the most spectacular event in the history of our galaxy, the collision of the Milky Way galaxy with the Andromeda galaxies. The question is, how did the scientists come to the conclusion that the galaxies are colliding with one another? What criteria do the stars of the Andromeda galaxy use to determine when they have arrived in our Milky Way? The most important question is, what will future generations, if they are still alive, perceive when the two galaxies come together? Let me begin by posing a question that a lot of people have. If the universe is expanding and galaxies are receding, then why is Andromeda coming closer to the Milky Way? It is possible for us to deduce the solution due to the fact that the gravitational pull between the two galaxies is larger than the influence of cosmic expansion on such short distances. Although galaxies in the remote reaches of the universe are experiencing a separation as a consequence of the expansion of the universe, this separation is most noticeable over extremely long distances that transcend tens of megaparsecs. Due to the fact that the Milky Way and Andromeda are traveling in opposite directions, it is inevitable that they will face each other regardless of the total expansion of the universe. When compared with the ordinary experiences that we have here on Earth, the concept of cosmic collisions is completely different. In the event that two cars collision on Earth, it just takes a fraction of a second. There is no notable difference between asteroids and other smaller space objects. Within a collision track, there is a specific moment at which two boulders will collide with one another and cause a collision. On the other hand, collisions in galaxies that contain hundreds of billions of stars take hundreds of millions of years to occur and are both dramatic and gradual. An intriguing example of this phenomenon can be observed in the Antennae galaxies, a striking pair of interacting galaxies located in the constellation Corvus. These galaxies are situated approximately 70 million light-years away from Earth, making them relatively close by cosmic standards. Currently, they are in the midst of an immense and dramatic collision, which has captivated the attention of astronomers for decades. The Antennae galaxies derive their name from the extraordinary tidal forces at play during their interaction. As these galaxies spiral towards one another, the immense gravitational forces exerted between them create vast streams of gas, dust, and stars that extend far beyond the galactic cores. These streams resemble long, delicate antennae stretching out into space, giving the galaxies their distinctive name. These antennae-like tails are not just visually stunning, they are also regions of intense star formation where the compressed gas and dust have triggered the birth of countless new stars. This cosmic dance is not a fleeting event, but a process that unfolds over an incredibly long timescale. Research has shown that the collision and eventual merger of the Antennae galaxies have been ongoing for at least 100 million years. This duration underscores the slow yet awe-inspiring nature of galactic collisions, which can span hundreds of millions to billions of years. Despite the seemingly slow pace from our perspective, the forces at work are anything but gentle. The collision will eventually result in the formation of a new, larger galaxy, as the two original galaxies merge their contents into a single, more massive entity. The Antennae galaxies offer a vivid illustration of the dynamic and ever-changing nature of the universe. They serve as a powerful reminder of the immense forces that shape galaxies over time, leading to the creation of new structures and the destruction of old ones. As we observe these distant interactions, we gain insight into the future of our own Milky Way galaxy, which is destined to collide with the nearby Andromeda galaxy in a similar cosmic event billions of years from now. Galaxy evolution is mostly caused by collisions between galaxies. Over the course of its existence, the Milky Way has been the site of a number of mergers and interactions. In the present moment, the Milky Way is tearing apart and absorbing the Sagittarius dwarf elliptical galaxy, which is an example of a substantial interaction. A portion of the expansion of the Milky Way's halo can be attributed to this ongoing process that has resulted in the formation of star streams. However, the most significant event that will take place in the future is the Milky Way's collision with Andromeda. An exceptional category of stars known as hypervelocity stars is the first piece of evidence that the Milky Way and Andromeda galaxy have begun to collide with one another. These stars, which are similar to cosmic shards, are traveling across space at such a rapid velocity that they are able to outrun the gravitational pull of their own galaxies. Consider the scenario in which a ball is thrown with such force that it flies into the air and is never seen again. There is a process that is analogous to this that takes place with hypervelocity stars, which accelerate to distances of approximately 1,000 kilometers per second. When traveling at a speed of 1,000 kilometers per second, which is over 3,000 times faster than the speed of sound in the air, it would take slightly more than 40 seconds to accomplish a full circumnavigation of the Earth. A question that has to be answered is how these stars are able to achieve such incredible speeds. The possibility of coming into contact with the supermassive black hole of a galaxy is just one of many possible consequences. In a binary star system, two stars orbit in perfect harmony, locked together by the force of gravity. This type of stellar system is called a binary star system. The idea will become clearer to you as a result of this. Imagine for a moment that this star couple is in a precarious position perilously close to the gigantic black hole that is at the center of the galaxy. The strong gravitational force of the black hole causes the binary system to be broken up, with one star being consumed by the black hole and the other star being hurled out of the galaxy at dizzying speeds. During the process of a star being expelled, a hypervelocity star is created. A star can be ejected from a binary system according to certain alternate ideas if the companion star goes supernova or if galaxies interact. In spite of the fact that the idea of a hypervelocity star has been discussed since the latter half of the 20th century, it wasn't until 2005 that scientists actually discovered one. The average number of times that a star is expelled from the core of the galaxy is once per 100,000 years. According to the findings of researchers, approximately 1,000 stars are believed to be flying across our galaxy at an extremely high speed. It is possible that some of them come from the Andromeda galaxy, which is a fascinating possibility and probability. It would be more appropriate to describe the difficulties of locating these hypervelocity stars amid the estimated 400 billion stars that make up the Milky Way. Analogy to a needle in a haystack would capture the essence of the situation. Even more difficult is the task of locating stars that have traveled through other galaxies on their route to the Milky Route. This is the reason why astronomers began by experimenting with models. The first thing that they did was investigate the relative movements of the Andromeda galaxy and the Milky Way galaxy. The next thing that needed to be done was to create a model that encompassed the gravitational forces of the system, taking into account both the visible and dark matter that was present in the galaxies. Under these conditions, the scientists carried out simulations in order to trace the paths that stars with hypervelocity would take once they were born. They simulated the courses of 18 million hypervelocity stars in two distinct scenarios, one in which the Milky Way and Andromeda have masses that are comparable to one another, and another in which the Milky Way has a mass that is nearly half that of Andromeda. The stars were started from random points around the center of Andromeda, and then they were directed in random directions. This was done so that the simulations would be truly accurate and thorough. After that, the crew utilized both mass scenarios in order to investigate the velocities of the hypervelocity stars as they proceeded into the Milky Way. In their research, they discovered that only a very small percentage of these hypervelocity stars were capable of reaching the region of the Milky Way. While the vast majority of these stars maintained their initial velocities throughout their journey, there were a few hypervelocity stars that slowed down to the point where they were engulfed by the gravity of the Milky Way. When we look at a sky map that depicts the current trajectories of these hypervelocity stars toward the Milky Way, we find that two different mass-based scenarios disclose the locations of these stars around the center of the Milky Way. Both instances have a distribution of stars that is as close to uniform as possible. However, in the scenario in which the mass of the Milky Way is equivalent to that of its host galaxy, the number of hypervelocity stars that are present occurs to be far lower. the Milky Way is able to capture a greater number of hypervelocity stars than it is able to do when its mass is 50% of that of the other galaxy. This is because the gravitational attraction between the two galaxies is stronger when they are of equal mass. In addition, the researchers compared the positions of the simulated stars to data collected from the actual world by the Gaia projects. This project is responsible for charting the locations and motions of stars in our galaxy. All indications point to the theory that the hypervelocity stars of Andromeda have moved to our Milky Way galaxy, as the comparison showed that there is a very close fit between the two stellar systems. According to the findings of the study, the number of Andromeda hypervelocity stars in the Milky Way might range anywhere from 12 to 3,910 at any given time. This conclusion was reached on the basis of the model assumptions regarding the masses of the galaxies. The findings demonstrate that hypervelocity star migration between galaxies is a genuine and quantifiable phenomena, despite the fact that the sample size was extremely small. Based on this, it appears that the Milky Way and the Andromeda galaxy have already begun swapping stars with one another. The halos that surround the two galaxies is the second piece of evidence that can be offered. The roughly spherical galactic halo of a galaxy is composed of both the visible and unseen components of the galaxy. Andromeda is surrounded by a large gaseous web known as the halo, which is named after the star system. The gaseous halo that surrounds it would appear to be around 3 times wider than the Big Dipper, despite the fact that people on Earth are unable to physically observe it. After discovering that mapping the halo of the Andromeda galaxy is notoriously challenging, physicists devised a brilliant solution to the problem. The 43 quasars that were situated behind the Andromeda galaxy were an object of investigation for the researchers. Quasars, which are extremely bright regions at the center of the galaxy, are powered by black holes. Because the 43 quasars that are dispersed behind Andromeda's halo are scattered out, researchers are able to explore different parts of the galaxy. Through the monitoring of the light that is reflected off of these quasars, the researchers may be able to gain knowledge regarding the spatial variability of Andromeda's halo absorption. Using Hubble Space Telescope data, researchers calculated that the halo of Andromeda extends 1.3 million light-years in our direction and 2 million light-years in every other direction. In comparison to what was initially indicated, the region in concern is significantly larger. Andromeda's halo contains an extent that is roughly equivalent to the diameter of the Milky Way, and it is estimated that it is located at a distance of 2.7 million light-years from Earth. A collision between the halos of the two galaxies has already begun, which is an indication that the epic collision is about to begin. Here we might be able to make out the intriguing timeline of events leading up to the Andromeda-Milky Way collision. The Milky Way and Andromeda will escape colliding with each other in a direct manner. A collision between galaxies is expected to take place for the very first time in around 3.75 billion years from now. When the galaxies first come into contact with one another, the enormous gravitational forces will cause a significant amount of disruption to the structure of the galaxies. What the sky would look like if there is a sudden explosion of star creation is as seen below. After their initial encounter, the galaxies will be thrown apart, but this initial encounter will not result in an immediate merger of the galaxies within the galaxy. Following the completion of the initial passage, the galaxies will continue to move closer to one another. This is the second passage, which begins 5 billion years from the present and continues for 1 billion years beyond that. At this point in time, the cores of the galaxies will proceed to approach each other more closely, which will result in interactions that are becoming increasingly intense. As they continue to spiral toward one another, the supermassive black holes that are at the center of Andromeda and the Milky Way will eventually come together at some point in the future. This second technique will result in a more intense level of star production, and it is possible that stars could be violently ejected from the combined system. At a time of 5.1 billion years, 2 dazzling lobes are representative of the cores of the Milky Way and Andromeda. It is inevitable that the galaxies will continue to move through one another, resulting in dynamic friction that will gradually deplete their energy. At the conclusion of this phase, the two galactic centers will have entirely formed a single entity. In contrast to the spiral galaxies that came before it, the expanding galaxy will most likely have a more elliptical form. This will allow the stars to find new homes inside the galaxy. At this moment, it is possible that our solar system has been thrown into space or thrown to a distant part of the new galaxy. After 7 billion years, the two galaxies will combine to form a huge elliptical galaxy out of their combined components. A heartfelt thank you for being here with us today as we come to the end of our journey at Spaceverse. Your support is what drives our investigation of the cosmos. Remember to hit the notification bell and subscribe to our channel so that you can continue to explore with us. See you until the next time we cross paths in the cosmos.